Record. Let's continue with chapter 6. Let's see, chapter 6. There it is. So we stop right here. We're talking about the magnitude and phase of the transfer function equations. So far, we have looked at first order filters, first order circuits, RL, RC, right? 2 circuits, 4 functions, depending on where we take the output. 1 energy storage element, so a first order circuit, first order filter. If we combine both of them together in one circuit, we get a RLC circuit or an RLC filter. RLC is a second order circuit because of 2 energy storage elements, and so it is a second order filter. Requires solving a second order differential equation. But we are not going to look at that. What we are interested in is the phenomenon of resonance. So we have R, L, and C. So as I was saying, circuit has R, L, and C, 2 energy storage elements, and they are connected in series. Ignore the output terminals. Output terminals are open. Only one connection shared between each component, so they are connected in series. And we get a series resonant circuit. Now, resonance is a phenomenon that you have seen, well, not seen at least, but be aware of that occurs in nature. You have mechanical resonance, right? In electrical circuits, the phenomenon of resonance causes voltages and currents that may be larger than the source to appear in the circuit. Okay, so electrical resonance, the phenomenon would cause voltages and currents that are larger than the source that would appear in the circuit. And one way that is possible is because of the energy storage capability of the inductor and the capacitor. So let's say the inductor and the capacitor charged up to a certain level, right? Now, you combine the stored energy along with the energy that is provided by the source, right? Vs plus VL or plus Vc could end up being much larger than anything Vs is providing. One of the reasons for that is because capacitors and inductors are duals of each other. So the energy is constantly flowing in and out of the inductor and the capacitor, right? In and out of the inductor and capacitor. Now, in a series resonant circuit, we don't have to worry about those kind of voltages or currents appearing all too often. But what we are interested in is basically the impedances of the inductor and the capacitor. Okay, so resonance is a phenomenon that occurs at one specific frequency. So when you have an incoming signal that has hundreds of frequencies, or if the frequency is varying, at one particular frequency, the impedance of the capacitor and the inductor are exactly the same. Or I should say, the magnitudes are exactly the same. Okay, so the magnitudes of the inductor and capacitor impedance are exactly the same, but the phase is exactly opposite by 180. And so they cancel each other out. Okay, magnitudes are exactly the same. ZL is plus 90, ZC is minus 90, and they are series, so they share the same current. So they're out of phase by 180. And so effectively what happens is that the combination of the inductor and the capacitor has equivalent impedance as 0 ohms. 0 ohms. ZL plus ZC, because it is connected in series. The equivalent impedance of a series connection of impedances is simply the sum, right? So ZL plus ZC goes to 0. 0 ohms is effectively a short circuit. So the combination of the inductor and capacitor behaves like a short circuit. 0 ohms. it is effectively no longer present in the circuit. Okay, it's no longer present in the circuit. So the only thing remaining in the circuit is basically the resistor R. So the total equivalent impedance that is seen by the source looking into the circuit, meaning the only load that the source is seeing, is resistor R. So whatever input we give, output would be at a max. So this is F, this is V out, this is max. For all other values of the incoming frequency, the output would be much less. Does that make sense? Right? And thus, we obtain a frequency response that looks like this. And that brings us to why we're interested in this, is because this is the characteristic of a band pass filter. It has a band of frequencies that are allowed to pass through. Everything else is blocked. Ideal band pass filter. This is the pass band. This is the blocked band. Everything in the middle is allowed to pass through. So this works as a band pass filter. Y-axis has the magnitude of the transfer function. Transfer function is ratio of output voltage to the input voltage. Output voltage would never be more than the input voltage. So maximum value is 1. And that would occur at a frequency known as F0, which is the resonant frequency for that circuit, and is given by this equation. F0 is 1 over 2 pi root of LC. It comes from the fact, mathematical derivation is you put ZL is equal to ZC. So you get J omega L, or J 2 pi FL equals J 1 over J 2 pi FC. F is set at the resonant frequency, and you can get an equation for F0. In terms of omega, omega 0 is simply 1 over root of LC. So if another student or professor talks about omega 0, they're talking about the exact same thing, because omega is 2 pi f. If you take 2 pi on the other side, you get 2 pi f0 is equal to 1 over root LC, which is omega 0, radians per second, but the same equation nonetheless. Make sense? Right? So at the resonant frequency, output goes to maximum. For all other values, the impedance of the capacitor and the inductor is going to cause a attenuation in the signal. So V out will always be less than V in. And hence we get the characteristic that is typical of a band pass filter that only occurs in a resonant circuit. If you look at this characteristic and we break it up, we can see that the first half is a high pass filter. The second half is a low pass filter. You combine them together and you get a band pass filter. You have a cutoff frequency here. You have a cutoff frequency here. The cutoff frequency for the high pass portion is FL. For the low pass portion is FH. Typically, some circuits or some problems might just say F1 and F2. But that L and H is just signifying the actual value, meaning L is closer to 0, right? So this first cutoff frequency or break frequency is closer to 0. So it's called as FL and FH. But in reality, that FL indicates or relates to the high pass portion, and FH indicates the low pass portion. And you combine these two together, you get a band of frequencies in the middle that are allowed to pass through. Make sense? Well, it's just because the actual value of this frequency is lower than this one. That's all. But as I said, some has the lower frequency. Yeah, so this here, the L and H is simply referring to the actual value. Doesn't indicate anything else. So as I said, some circuits you might just see F1 and F2. That's all you would see. Now, if you take these two and you design the high pass and the low pass cutoff frequencies that are opposite, what do you get? You get a band stop or a band reject filter. So you have FL and FH here, you cross them over, or you design it in such a way, you get a band stop filter. So the low pass is here, and the high pass is here. When I say here and here, I'm not referring to like a physical connection. It is the value of the break frequencies. Okay, it's the value of the break frequencies that need to change. Physically, you can take two filters and you can cascade them, meaning you can connect the output of one filter to the output of the next. And it typically does not matter which one comes first or which one comes second. Okay, electrically speaking, it doesn't make a difference. You can put a high pass before a low pass. You can put a low pass before a high pass. But what matters is the value of these frequencies. So those frequencies depend on the values of the components, right? We saw it in the first order filters. We take two of those filters together, we cascade them, and we get a series resonant circuit. So this would be a band stop filter. Okay, band stop filter. There is a quality factor associated with the circuit. It is still noted by Q. Q stands for the quality, but this is not the Q that is used for inductors and capacitors, excuse me. The subscript S notes that it is for a series resonant circuit. So QS refers to a series resonant circuit. In terms of the components, these are the two equations. But more importantly, we want that band to be as narrow as possible, right? So real life filters, as an example, if I want to tune my radio to 99.7 megahertz, the radio station, I want only that frequency going into my device, right? I want the filter at the front end to block out everything else. In real life, it's never possible to just design a filter that would allow only one particular frequency. There'll always be a band around that frequency. So 99.7 filter is still going to allow certain other frequencies right next to it to actually go into the device. So depending on how wide or narrow the band is, we define the quality. And that is defined by this equation. QS is F0 over B, where B is the width of the band of the frequencies. So FH minus FL is the band width, the width of the band. And quality in terms of the bandwidth is given by F0 over B. The narrower the band, the higher the value of QS. Which makes sense, right? Because that is what we want. If quality is very, very high, we would have a very symmetrical waveform. You would have a very symmetrical waveform centered around F0. And then we can say that FH and FL are equidistant from F0. Okay, if this is high, typically I would say higher than 10, but conservatively I would estimate like 5. If it's higher than 5, then you can have a symmetrical frequency response. If it's symmetrical, centered around F0, we can say FH and FL are equidistant from that center. Okay, that's the series resonant circuit. To also look at it another way, we saw a RC filter first. Remember, the first filter we saw was a RC filter. where you took the output across the capacitor. Remember what kind of filter it was? It was a low pass filter. If you take the output across the inductor, you get a high pass filter. If you take the output across the resistor, you get a band pass filter. So this is two filters combined in one, because if you remember, this was the RL filter. This was the RC filter. The schematic representation of the drawing does not matter. This is just for convenience purposes because you want to take the output across the resistor. But this is still a RL filter. This is still a RC filter. The fact that we're combining those does not make the operation any different. So if you take the output across the capacitor, you get a low pass filter. If you take the output across the inductor, you get a high pass filter. Output across the resistor, you get a band pass filter. Right? If you connect all of these in parallel, you get what is known as a parallel resonant circuit. Operation is exactly the same. Everything works exactly the same. At resonant frequency, magnitude is exactly the same. And so ZL plus ZC again goes to 0 ohms, but this time they're connected in parallel. So the total equivalent impedance of the inductor and capacitor is ZL times ZC divided by ZL plus ZC. If ZL plus ZC is 0, what can we say about ZLC? Infinite. It goes to infinity. If it's infinity, then the combination of the inductor and the capacitor is effectively behaving like an open circuit. It may as well not be present or part of the circuit. Okay. And the only thing left in the circuit is the resistor R. And that resistor R will have the maximum current flowing through through itself. And so output voltage once again goes to maximum. And when it goes to maximum, we get frequency response that looks like this. Again, exactly the same. Everything still stays the same. Value for F0 is still given by 1 over 2 pi root LC. All of these equations are still the same. The only thing that's different is the notation for the Q, which is now QP for parallel. And in terms of the components, QP, the equations are now flipped. It was 1 over 2 pi FRC. Now it is 2 pi FRC or F0 RC. And this was divided by R. Now it's R divided by. So everything's flipped. Okay, everything's flipped. All right, questions? Any questions? Look familiar? Loudspeakers, right? If this doesn't look familiar, then you need to get out a bit more. Perhaps during spring break. What is this speaker called? The small one. This is mid-range. What is this one called? Well, not quite sub, but just a woofer. Subwoofer would be even lower than, because it reproduces sub frequencies that are, well, sub as in under frequencies that are under. So woofer would typically, reproduce frequencies that are higher than 200 hertz, which is on the low end, the loud thumping noises. So these reproduce low frequencies, the bass sounds. Mid-range is for vocals, and tweeter reproduces high frequencies. And the reason, of course, is that the lower the frequency, the longer the wavelength, the bigger driver that you need. So the lower frequencies need as big a cone as possible to move the air. The smaller frequencies, not so much, because they don't travel as far. Subwoofers reproduces, so the bigger the cone, the more power it needs to actually move. So if you ever see a woofer or a subwoofer in action, you can put your, you can touch it and you can see it's just, bouncing, physically actually moving. So there are some subwoofers that, and so subwoofers by themselves need extra power. So they are a separate piece of equipment. Home theaters in a box, just crappy. I mean, you cannot provide enough power. Anyway, how many of you have a subwoofer in your car? Anyone? Just one? Now, when I was a student, I didn't have a car. Okay, so when I went to grad school, and I picked up like an old one, like a junk piece from Lock Auction, a car auction, and I bought like my first car for like $1,000. And then I went to Walmart and I picked up a dual subwoofer box. So I had two rocking in my car. Again, not expensive, cheap, so about $150 or so, but they work very well. So hopefully one of the, once you get a job, you graduate, go and rock the cars. Now, yeah, you got to live a little, right? What they say about engineers, you work very hard and you play very hard. So the way this relates to us is this is a real life example of a filter circuit. If you look at the back of these loudspeakers, if you look at the back of any of these speakers that are mounted on the wall or on the ceiling here, you will see one cable going in. You'll see one cable going in, right? That one cable has two wires, plus and minus. But it is connected to all three of these drivers, all three of these speakers, right? And each speaker has a specific function. The woofer reproduces only low frequencies. This reproduces only mid-range or band of frequencies. This reproduces only high frequencies. So this requires a high pass filter. This requires a band pass filter. This woofer requires a low pass filter. And those are very easy to implement. Even a really cheap, inexpensive computer speaker, if it's two-way, even if it's not two-way, it's very easy to connect a filter in there. I've seen speakers which have like a RC, like a resistor and a capacitor, without a circuit board. It's simply like two components twisted together, and the wire is connected at both ends, and it goes into the speaker. No circuit board required. Expensive ones like these, if you open up the back, which is not difficult to do, you would see a cable going into a circuit board, and that circuit board might have a heavy coil, would have a few resistors, a few capacitors, and have two inputs, which is basically the inputs that are coming from your system. And those two inputs, one single input is split into three, and each one is connected to that filter output. And this is known as the crossover network. So in spring break, over spring break, go to a party, take a screwdriver with you, open up the back of one of these loudspeakers. You can have a screwdriver in both hands. All right. So that's a real life example of where you would see an electronic filter like this. But in this modern day and age where we have all of these electronic devices, all of these devices work on wireless signals, and they all have filters at the front end. That's the absolute first thing that is at the front end. You do not want any unwanted signal going into your circuit and messing things up. Okay, let's get back to our and continue with the last topic, which is Bode plots. Okay, Bode plots. H.W. Bode was a researcher who came up with a method to graphically plot the frequency response of circuits, specifically filter circuits. Okay, what it does, what the plots do is basically plot the magnitude of the transfer function, the y-axis, as a function of frequency. Now, the problem with that is that the frequency range is very vast, right? You have frequencies going, we just talked about, like low frequencies, tens of hertz, going all the way to megahertz, gigahertz, and terahertz. So starting from like, 1 or a few hertz, like tens of hertz, going up to 10 raised to 6, 10 raised to 9, 10 raised to 12, and even 10 raised to 15 now. Okay, so trying to plot all of that vast range or wide range into one single chart is an impossible task. On the other hand, on the y-axis, you're trying to plot the voltages and power on the y-axis. They also have a very large variation. You would transmit a high amount of power at one end, and you might receive like milliwatts at the other end. So trying to quantify and put or plot both of them in the same plot is very, very difficult. And so what Bode plots do is it allows us to plot a very wide range of frequencies on the x-axis and a very wide range of values of the magnitude on the y-axis. And the way we do it is we compress it by using the log scale. Okay. So let's first look at the x-axis. On the x-axis, we plot the frequencies by number of decades. Okay, by number of decades. A decade simply is the log of the ratio of any two frequencies. Okay, you take any two frequencies and you take the log of their ratio. If the base of the log is 10, that number, it gives you a decade. If the base is 2, it gives you an octave. You might have heard octaves typically when you talk about like artists who are singing, like vocal artists. It's sometimes you would see it referred to as this specific artist can sing in this range of octaves. Well, that's what they're talking about. The range of frequencies that the artist can reproduce. Okay, that's the octaves. But Bode plots, they plot the x-axis frequencies in the number of decades. So one decade, for example, goes from 10 to 100. Ratio of 100 to 10 is 10. Log of 10 gives you 1, so 1 decade. On the other hand, if you go from 10 to 1000, the ratio is 2, or the ratio is 100, so log of 100 gives you 2. And so this is 1, this is 1, this is 2. And thus you can take your scale and you can compress it. So x-axis is now compressed. And you get what is known as a log graph, a log chart. How many of you have used this before or seen this before? 1, 2, 3, 4, 5, 6. Good. So this is not just for electrical engineering, obviously. It's all scientific and engineering fields. If you want to represent a wide range of data on a single piece of paper or single chart, you use a log scale. If both the x and the y axes are in the log scale, you have what is known as a log chart or a log graph. If only one of the axes is in the log scale, as in this one, the x-axis is on the log scale, the y-axis is linear, so then we have what is known as a semi-log chart or a semi-log graph. Okay, and it's log because physically the distance between each division is a direct relation of the log of that number. So going from the first one to the next, it is log of 2, log of 3, log of 4, and so on and so forth. There is no 0, of course, right? There's no 0 because it's a log scale. So you go from 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you change and jump to the next decade. So it goes 10, 20, 30, 40, 50, 60, 100. Jump to the next decade, goes 200, 300, 400. So 10 raised to 1 is the multiplier. The exponent is the multiplier. Linear scale, we add. Log scale, we multiply. So here, if I start off with 1 hertz, the first decade is the units or the numbers multiplied by 10 raised to 0. And you get to 10 hertz. Then the multiplier is now 10 raised to 1. 10, 20, 30, 40, 50, 60, 200, 100 hertz. Now the multiplier is 10 raised to 2. 1,000. 10,000. And 100,000 hertz. Right? 10 raised to 5. So going 10 raised to 2, 10 raised to 3, 10 raised to 4, finally the next one. So if I wanted to add on, I can keep extending the line. It's a multiplier. In the linear scale, we add, log scale, we multiply. So we're going all the way from 1 hertz to 100,000 hertz on the same chart. X-axis is now compressed, right? So if I wanted to plot, I could plot everything in range. Make sense? Again, if you have not yet encountered this in your fields, at some point in your career, you would, as either as a student or as a working professional engineer. At some point you will. So that's what log scale is. Right? Then the y-axis, they're trying to plot the power, right? So telephone engineers early on were trying to quantify the power loss that occurred during transmission. So at one end, they were transmitting certain amount of power. At the other end, they received very small magnitudes. So to try to quantify, try to quantify that power loss in transmission, they came up with a new unit. The new unit was again log of the ratio of the two powers, and they named it as Bell. Named it after a person. Any guesses who? Telephone engineers, unit of Bell. Alexander Graham Bell, named after Bell. So 1 Bell, uppercase B, again, different from what we learned in electromagnetics. Uppercase B is log to the base 10 of P2 to P1, and that's defined as 1 Bell. Even that 1 Bell was not sufficiently small enough, so they put a unit prefix in front of it. Unit prefix is 10 raised to -1, 10 raised to -2, 10 raised to -3. If you remember from the first day of class, 10 raised to -1 is deci, 10 raised to -2 is centi, 10 raised to -3 is milli. So you break up 1 Bell into 10 parts, you get 1 decibels, or more commonly known as dB. Lowercase d, uppercase B. So 1 dB is used to quantify sound. It simply is 10 times log of P2 to P1. Log of P2 to P1. So the ratio of the powers. For a normal normal human ear, the perceptible level is 3 dB. So if you have a audio system, sometimes instead of just numbers, that display would give you the level in dB or decibels. If you want to increase the volume, a perceptible difference has to be at least 3 dB for normal people. For me, it's like even higher probably. But the power that is outputted by the amplifier needs to double, because again, it's a log of the ratio of the two powers. So if you want to increase or decrease the volume by 3 decibels, which is what a normal human ear can discern, then you need to double the power. Yes. Yeah. That is a huge amount of, you would have, so there is a chart that I use in E classes where the sound of a train whistle, or I can't remember, some of the common sounds, they go up like 100 decibels. Yeah, very, very loud. I don't know. You're asking, because that is subjective to every person. right? Some people have very sensitive ears, and so they would be able to discern even very low changes in volume. Other people like me who are, already have bad hearing, you would need a much larger change in volume. So that is very subjective. It depends on each person. But just technically speaking, it would need to be, technically speaking, obviously, again, if we just increase it by 1 dB each, some people may be able to hear. But the point in terms of power is, if you want to increase the volume or decrease the volume, a normal typical human ear can discern a 3 dB change. So if it's 1 dB or 2 dB, most people may not be able to hear it. Most people would require a 3 dB change, but a 3 dB change requires a doubling of the power. And that's the important point. You would need to double the power output to change it at least 3 dB. More importantly, the way it pertains to the plots, the frequency response plots the magnitude of the transfer function. Transfer function is V out, V in, right? Ratio of V out to V in. So it's V out divided by V in. Ratio of voltages. Power is V square over R. V square over R translates this equation, or this equation right here, decibels, to 20 times log of V2 over V1. Okay, ratio of the powers, 1 dB is simply 10 times P2 over P1, but in terms of voltage, it becomes 20 times V2 over V1, or log of V2 over V1. So when you plot the magnitude of the transfer function of any filter, if you're taking V out to V in, it is 20 times the log. So now if you plot a Bode plot, both axes are compressed. X-axis, you take the values as they are, the linear values, and you plot them on the compressed X-axis. So the values are plotted here on the X-axis, frequency is plotted on the X-axis, but the scale is compressed. And the scale is compressed here. On the Y-axis, the scale is linear, but the values themselves are compressed by plotting them in decibels. Does that make sense? And thus both axes are now compressed. And so you get what are known as Bode plots. Bode plots are straight line approximations of the frequency response of a filter. And so if you have a low pass filter like this, you can approximate it by three asymptotes. A high pass filter similarly can be approximated like this. So this would be low pass, this would be high pass, straight line approximations. So these were very useful in the days when we didn't have computers to plot everything. They're still very useful to engineers now. Okay. And the slope of these filters is always 20 decibels per decade of frequencies. For every decade change in frequency, the value either increases or decreases by 20 decibels. And this is for a first order filter. First order filter. So first order filter is 20 dB per decade. Second order filter is 40 dB per decade, much steeper, and then so on and so forth. You go to higher order filters, try to approximate the slope as close as possible to a vertical line, meaning an ideal response. Again, filter design is a whole different specialization within electrical engineering. There are many trade-offs, but that's what Bode plots are. And with that, I'm going to say chapter 6 is at an end. Questions? I'm sure you have a lot of questions. It's a lot of material being thrown out. I mean, thrown at you, not thrown out, but thrown at. Any questions at all? So announcements. If there are no questions, I have to make a few announcements. Any questions? No questions? Okay. Well, first, the good news. I will not test chapter 6 on the final exam. Okay. There are 3 assessments, meaning 3 homework assignments for the final exam. I mean, for chapter 6. I wish we could have done a quiz, but it's okay. I mean, we did 7 quizzes. That's equal to like 2 midterms at least in the entire quarter. So chapter 6, 3 homework assignments, I feel is sufficient enough. I will not test it on the final exam. So I will update the final exam page and I will remove that problem from there, right? Whatever is left on there will be the updated. Saturday final is going to be in room 126, which is opposite my office. If you are checking the lab, I think almost all sections except 2 take place in that room. So if you're taking the lab in that room, you already know where that is. On Saturday, I will make sure that the building is open, and well, I'll prop it open if it's not already open. Let's see what else. Yes, homework. So AC power, I extended up to today, but in the previous section, I said I'll extend it up to tomorrow. So if you have not yet done AC power, which is going to be tested on the final exam, will be due tomorrow. And late homework is accepted, so you can still, submit it anytime you want, with a little penalty, of course. Chapter 6, 3 assignments. The first one, again, I will make it due tomorrow, which is the transfer function. And the second and the third ones, I moved it all the way back to Sunday, the Sunday before finals. Now, obviously, don't wait until the last minute to get it done, but I extended it so that students have time to get it done, right, without any penalty. Get as many points as you can get. Let's see what else. Those are the homework assignments. If you have not yet uploaded your homework scans, which several students did not realize that they have to, despite my reminding them, during the quarter, you still have time. There is no penalty on it as long as these assignments are submitted before the end of the quarter. So please make sure you go ahead and upload those assignments. Let's see. Second part of the good news, no class on Friday. There is no need for the class on Friday. So take the time off to study, take the time off to prepare, meditate, sleep if you want. Get caught up on your sleep if you want, which is always at a premium. So I will be available. Office hours, I will be in person. In my office, I'll hold Zoom office hours. If you wish to see me on Zoom, just send me an email. I'll be available all through finals week. I'll be available on Saturday in person as well as on Zoom. I'll be available on Sunday. Sunday I have something in the morning, but I'll be available Zoom for the rest of the afternoon all the way to the late evening. I'll be available Monday, Tuesday, Wednesday, Friday, Saturday also if you want. Okay, I'll be here I'll be here pretty much all March long, Monday through Friday, 8:30 to 4:30. I have no life. So I'll be here every day, right? Even if you want to talk about this class or something else, I'll be here. Let's see what else. Those are the announcements, the final exam, the location. If you are taking the exam other than Saturday, it is in this classroom, 125, in this classroom. Let's see. If you have not yet filled out, if you are planning to take the final at its regular scheduled time, you don't need to fill out the form. But if you're taking it at an alternate time, you do have to submit the form. Let me know. And then one final thing. One final thing is evaluations. So as always, my goal for every quarter, for every class that I teach, is to ensure that every student learns something. Well, I would hope they learn a lot, but my goal is always to ensure that every student feels that when they leave my classroom at the end of the quarter, they are a better engineer and they are more knowledgeable when they first walked in, right? So if that goal, that's my goal every quarter, I feel that I try to accomplish that every quarter, and I feel that I've done it this quarter too. Hopefully you feel the same. Fill out the evaluations that are now available. This is the only thing that we see at our end. Okay? This is the only thing that we see at our end, which is the number of students who have submitted the evaluations. So I'm very happy with the response. I haven't even talked about it yet, but I'm very happy with the response. So let me see so it's 14 of 34. Yeah, 14 of 34. In case students don't remember, there's extra credit built into the course a lot, homework assignments. And then the final piece of extra credit is with the course evaluations. So we don't even get these until, after spring break. So it's like the quarter ends, everyone goes on break, and then the staff somewhere in the university, administrative staff, puts it all together and they deliver them to us. And the only thing we see are basically the numbers and basically anonymous comments. That's all we see. So before this closes on Friday at midnight, whatever number is here, every student in the class receives that amount of extra credit. So if this number is at 17 of 34, that is 50% response rate. So every student in the class receives 0.5 points applied directly to your final grade. If everyone participates, and this number is 34 out of 34, it's 100% response rate. Every student gets 1 point of extra credit applied towards your final grade. If you get an 89 and you're stuck at B plus, this will push you up. And if it's like 1, this will push you up to like 90. So there's a lot of extra credit built into it. So I like to say the curve is already built into it, into the system. Any homework assignment extra credit that you did is carried over. So every single homework assignment has some extra credit. All of that extra credit points is carried over to the entire homework category. And whatever is left over is also carried over to your entire course grade. So if you did, and I pointed this out at the beginning of the quarter, it's also there in the syllabus. If you performed all the extra credit assignments and you have extra points, they will offset your losses in other places. I always have students at the end of the quarter who earn more than 100% overall grade. Always had some students to do that. And there are several students who are on track to achieve that. Of course, it also depends on the final exam, but there are several who are on track to do that. So I do not curve. I do not just credit after that. It has to be fair and equitable to everyone, meaning if I provide an opportunity for extra credit for some students, I have to provide it for all, right? Otherwise, it's not fair to everyone. And so this is provided. Whether you participate or not, you do get the benefit. Every student gets the benefit. That's the purpose in showing these. Now, I'm not just showing numbers. I'm showing this is anonymous. We don't know who's filling it out. We only know the response rate. We don't know who has filled it out. We do not differentiate between any student. There's no way for me to know which 14 students have filled it out. There's just no way. Okay, the system does not capture that. And I have no interest in knowing that either. So whatever the response rate is, every student gets that extra credit. Right. So go ahead and fill out that evaluation when you time. I know you have very busy lives, especially at the end of the quarter, but I wish you all the luck. I will see you on finals and all the best for the rest of your finals. If you have any questions, I'm always around in my office, over Zoom, anytime you need. All right. It was a genuine pleasure to be in the classroom. I really like being with students. I don't like doing research a lot. I like doing research without any pressure. So I like doing research without any pressure. I like being in the classroom, and I love teaching hands-on work in the lab. So it's a genuine pleasure. And well, I'll see you all on the day of the final.